Hey kids, Smath here. I want to talk to you today a little bit about delta G. Delta G, free energy. This one we defined, this is our energy to do work, to perform work. And for our purposes, in chemistry for the most part, we're looking at delta G is going to come from a couple of different places, but delta G is equal to delta H minus T delta S. Goldfish are heck without tartar sauce. There's your goldfish. Goldfish are heck without tartar sauce. That's just an easy way to remember that, but it's a pretty easy equation to remember anyway. So delta G, delta H minus T delta S. So what we look at here is if we're given some values, we're looking for a negative delta G. That's going to be a spontaneous reaction. So if we're just told that H is 40 kilojoules, and we're going to run this at a temperature of 130 Kelvin, and S in this scenario is going to be 0.300 joules per Kelvin. Just a heads up, kilojoules per Kelvin. That value for S is usually going to be given as 300 joules per Kelvin. And then we've got to convert that. And I think it's a lot easier if we just convert the S to kilojoules rather than the H to joules, because H's and G's, these are big numbers. S's are small numbers, but we're going to multiply it by a pretty large temperature here. Now, let's face it, 130 Kelvin, not very impressive. Let's see what we find out. If we calculate this, we find out that delta G is going to be positive 1 kilojoule. This is going to be a non-spontaneous reaction. And that would be case number one, where if this was what happened, we have a non-spontaneous reaction. Well, what's going to happen if we're able to change that temperature just a little bit? And in this case, all we have to do is take that temperature. Let's keep delta H the same. Delta H is going to be 40 kilojoules. That doesn't change very often. Minus a temperature that goes from 130. Now, we're going to kick that temperature up a little bit to 150 degrees or 150 kelvins, all the while keeping our entropy the same at 0.3 kilojoules per Kelvin. And now, all of a sudden, what used to be a positive delta G, non-spontaneous, now becomes a negative 5 kilojoules. And that becomes a spontaneous reaction. And so as we increase the temperature, and when we think about that, we have delta H that's positive. That's a positive delta H value, endothermic. So what we're saying is, if we increase the temperature of an endothermic reaction, it's going to become more spontaneous. We already knew that. We already knew that, kids. In an endothermic, positive delta H, if we were to write a reaction, we would say A plus B plus energy is going to make some form of AB something. Well, if H is positive, it's endothermic, so increasing the temperature is going to make the reaction occur more spontaneous, or as we've said historically, shift to the right, shift towards the products. Now let's see what happens if we take this and make it exothermic. So now in C, we're going to take and make our H a negative 40 kilojoules minus, and we're going to make our temperature back down. Whoops. Come back. We're going to make our entropy we're going to keep our temp. Sorry. Technical difficulties, my apologies. 130 Kelvin. And now let's keep our entropy, as we shift our entropy and make it a negative 0.3 kilojoules Kelvin. Get this cleaned up for you. Sorry. There we go. So delta H minus T delta S. And in this case, we end up with a value that's just barely negative, a negative 1 kilojoule. We've got a spontaneous reaction. Now that's pretty unique. We had a negative, an exothermic, but we also had, a negative, all right, something that's becoming more ordered, but is giving off energy. That's going to be spontaneous. And so if we look at this, now if we crank up the temperature, okay, now let's take, same scenario, D. We're going to take our negative 40 minus, let's increase the temperature of this, 150 Kelvin, keeping our entropy negative, kilojoules per mole, kilojoules per Kelvin. I don't have this one done. Bear with me for a moment while I calculate it. We're just going to say 150 times negative 0.3 gives me that. We're going to have negative 40 minus a negative 45. Holy cow. This just became non-spontaneous. So it went up positive 5 kilojoules. Now we went non-spon. Well, we increased the temperature. Yeah, but in this case, remember, we had negative entropy, negative 300. Now let's see what happens when we flip the entropy. This is our last scenario where we're going to keep it exothermic, negative 40 kilojoules, minus, let's go with the lower temperature, 130 Kelvin, and let's make it positive 0.3, 300 joules Kelvin. Grab our calculator and go 130 times 0.3, and now we go negative 40 minus a positive 39, and now we have something that's very spontaneous, negative 79 kilojoules. This is our delta G, very spontaneous. And so what I've just shown you is there are two scenarios where we can have the spontaneity flipping because of the temperature increase or because of the entropy increase, whether things are becoming ordered or more disordered. Let's look at another case where that happens. I've got a real simple example here for you. We're going to take a little bit of water, and that water is going to be a liquid, and we're going to make that water into a gas. We're going to vaporize some water. Put some heat into it. Well, let's see what that energy takes. If we take a delta H of 44 kilojoules, where'd we get that from? We could look that up in the back. We could have done products minus reactants, done standard enthalpies. Plenty of places to look that up. Next to those standard values in the back of your book, delta H, there's also a delta S column. And delta S for this reaction is 119 joules Kelvin. And what we want to know is calculate the energy, calculate T when this reaction becomes spontaneous. Okay, so delta G equals delta H minus T delta S, no problem. We're going to set G equal to 0 and then say 44 kilojoules minus T 0.119 kilojoules Kelvin, get my units working out, and say that we're looking for an answer where T is going to be greater than or equal to about 370 Kelvin. No kidding. We know the boiling point of water is 373 Kelvin. So this reaction shows us that when we take the energy, the temperature, and increase that to make T delta S bigger than delta H, G becomes negative. Negative G, spontaneous. So I've shown you some delta G equals delta H minus T delta S. And I've shown you how to use that calculating whether it's spontaneous or not. And we just did one where we can calculate the temperature at which it becomes spontaneous. I'm Smath. I hope this video helps you. I'll see you in the rooms.